with C block. And so we did some problems, and your job is to watch it tonight to review for the test, okay? So, but real quick, because we're going to work on lab most of the day, is the questions that are on the test. Yes, thanks. I just got to stop by to find out how yesterday was. After school, the meeting. Didn't you have yours after school? Yeah. So the first type of problem will be a modeling one. And we did a lot of different things with modeling. You did a whole discussion on the solar system one, and you did we did the demo where we came up with our own model, an inverse square model for with the lights. But this problem's going to be on a linear one where you have to find the slope. Yes. Yes. You'll have reference sheets on the test or for the test. Okay? The reference packet, your reference table. Did Jack show up or is he out today? Linear modeling, you'll have to find the slope with units, what the y-axis represents, what the x-axis represents, develop the equation y equals mxb, but with the appropriate symbols and the appropriate units, maybe do some interpolation, and maybe do some extrapolation, okay, like we did with the lab. Then you'll have a problem with conversions, and you'll have one where it's like converting maybe like miles per hour or some similar thing to standard units. So you'll have to know what your standard units are. In that case, it would be meters per second, right? Kilograms for mass, meters for length, seconds for time. And then you'll have also a conversion one where you have like a square or a cube in it. And you remember if it's like grams per centimeter cubed, and you wanted to bring that to kilograms per meter cubed, you'd have to do the centimeter to meter conversion 3 times. Okay? And I go over one of those in the video on miles squared. Then you find the x and y components of a vector. Then you do the graphical, addition of vectors, and then the mathematical addition of vectors. So the graphical addition of vectors, that was the one where it's like you have, no, that's the mathematical one. The graphical one is when you have the scale and the protractor and the ruler and the map, right? And so you take, like, the first vector is 20 meters long, but 20 meters, 5 centimeters equals 1 centimeter, so then you do that conversion and you measure it and you use the protractor and you draw it on there. Then you take the next one, say it was 30 meters at 145 degrees, and you measure that and you put that head to tail, and then you draw the resultant in from start to finish. Then you measure the resultant and you use your scale to convert that to meters or kilometers, whatever you're using, and you measure its angle to know its direction. We're going to do one like that in a second. And then the mathematical addition of vectors, did everybody get this written down? Well, you can get it online. Okay, so, wait, where'd it go? Whoops. Don't tell me I lost the whole thing. No, here it is. Is it? No. Oh, this is it. the mathematical addition of vectors. We have A, B, and C. You don't have to write all this down because it's going to be in the video. I'm just going to catch you up to real quick, okay? Then you write it down tonight when you're studying, okay? Or later today during study hall. You have A, B, and C. The first step is to find the components of each. A cosine 30 to get the components. A sine 30 to get the y components. So we have three vectors, A, B, and C, and we're adding them. And we find the x and y components of each. That's step one. What's step two? What? Add the x and y components. So this is what I wrote down when the fire bell rang, R. But Rx would be 17.3 for the AX component. There's no, so this little one right here, this is 17.3. There's no BX, and then CX is 12. Wait, no, CX is 32.9. Thank you. And then adding those together gives 50.02 for our Rx meters. Our Y, same way, but the Y's, we have 10 meters, we have 20 meters, and we have 12 meters. Even I can sum this in my head. 52, right? I was just kidding. So all the Rx's give you a vector. And when we arrange Rx that we sum together and Ry that we sum together, and we put them at 90 degrees head to tail, we can see our resultant vector is like that. And how do I go about finding the value of that resultant vector? Third step. Yeah, we p-thag it, right? Uh-oh, uh-oh. She said that's a what? Oh, yeah. Don't tell her I did that. She'll be mad. Okay, blame it on Miss Coons. Did you get 42.84? Oh, square root of that. Did you get 65.5? Oh, round to the 10th unless I tell you differently on this, okay? To the 10th. So 65.5 meters. But we need its direction as well. So we are going to find this theta right here. And that theta, we know this, Ry at Rx, so theta is just a tan inverse. I like to simplify it and just remember it's y over x. Like that. So tan inverse of 42 meters, but they're going to cancel, over 50.2 meters. Remember, you use inverse tangent, inverse trig functions when you want to find the angle. You could, since you have all sides here, you could use any, but we just, tangent always gets left out, so, 42 divided by 50.2, tan inverse, 39.9 degrees. Putting that all together, it's 65.5 meters. That's the sum of our three vectors, A, B, and C. Okay? 65.5 meters at 39 degrees. I could say either, because the resultant means sum. So the vocab you need to know is like extrapolate, interpolate, resultant, but it will come up by just knowing it like that. On this test, you're not going to have any multiple choice. You're just going to have problems to work out. I only have 2 short periods to do it, so I want to make sure that everybody can finish the test. Okay? Although, when do we meet? I think we're last period, second to last. So, you don't want to be late to the class, right, to start it. And you don't want to come in all frazzled and everybody's already working, because what does that do to your stress level? Way up, right? So, if your history teacher feels like it's necessary to keep you 5 minutes after to discuss something or other, you make sure you tell them you have more important things to do, like science. No, I'm just kidding. Of course I'm joking. So, I'll try to make it so that you can finish it. All right? No, they usually have part multiple choice and part problems on there. And the multiple choice usually relate to the chapter block, but in this case, I want you to get these problems down and not have to remember a lot of stuff about moon diameters and stuff like that. So that chapter block was more for your interest in understanding of development of scientific models and thought experiments and stuff. But I'm not going to test you any on that. The modeling questions is the linear modeling, coming up with an equation of a line, yeah. So we did other stuff with that, but what type of problem I'm going to ask you is that. Yes. Well, I don't know. I gave you the questions that are on it. How long will it take you to do those 5 questions? 100 hours? Well, you'll have about 40 minutes. No, I mean, there might be like 2 conversion ones. But then you realize some of these problems are longer, right? So I can't give you like 3 vector problems, right? Yeah. I usually don't have that problem. So like in your math test and 3/4 of the people are sitting there and they take the math test? So that's usually not an issue. Sometimes it is. You have to know, I mean, sometimes it is with students because they work slower than everybody else, so, or than other people. Some people, by the way, if you feel like you're always in that situation, there may be reasons for it that aren't really a reflectance of your intelligence, but maybe more, so speed. So sometimes people take longer on tests for a variety of reasons, and they can actually test to see if you fall into that category. And if you do, then you could get tested and get extended time on your test, and you can get extended time on SATs and all of that too. But you can't just be slow and lazy. There has to be reasons for it. I don't exactly know all the reasons, to be honest with you, but if you feel like you're constantly the last person on the test and stuff, you might want to, look into that further. Because it will negatively affect your SATs and all that. And it's possible you could get extended time. Okay, well, I'm sort of debating, but I guess we'll go over a graphical one. And we still have to play some vector tag games. Who's played 2 games? A couple of you. We're supposed to. Yeah, so the hope is to get to that. Because I have your due date for that lab on Tuesday. So I was hoping to get all your data done today so you could work on it over the weekend. But I started on rants about things like extended time. I'll never get out of here. And Lorene is disturbing our class. I'm just kidding. All right, so let's say you had graphical, and let's say we had a little map. I'm just making this up. And it's got a lake. Okay. Over there's Tommy's cabin. Okay. And Tommy walks in the woods from his cabin. I have a scale here. And we'll do 1 centimeter equals 100 meters. And let's say that Tommy walks 500 meters north from his cabin. Then walks 600 meters at 200 degrees. Then walks let's say 300 meters south and runs into Annika's cabin. What distance did he walk? And what is the displacement of Tommy's cabin to Annika's cabin? Magnitude and direction. Okay. So now your ruler's not going to work so well on this because I'm making it up and I'm using a fake centimeter ruler, right? I have this thing and a protractor. Okay. That over there till we need it. I'm going to make this a little smaller. Now, so the first thing that he did was what? No, 500 meters north, right? So starting at his cabin, I'll rotate this around. It clicks into place north. Whoops, he went off the map a little bit. Well, that's all right. I'll just shrink this down. That's better. Right, because 500 meters, our scale is 1 centimeter. So 500 meters, 100 meters is 1 centimeter. So that's going to give us 5 centimeters. Oh, 5 centimeters, okay? So that first walk goes like this. Then his next walk is 600 meters at 200 degrees. So 600 meters, if I convert that to centimeters, I know it's easy to do, but I'm just doing it in case, you know, you need to do it tomorrow. That's 6 centimeters. But I have to get the angle. Now the angle is, you go to the arrow, the tip of where he left off, and he's going to walk, how much? 200 degrees. So 200 would be, let me make this so we can look at it. This is 180, that's 90, that's 200, right? 0, 90, 180, 190, 200. So I'm going to make a little tick there where the 200 degrees would be from that. And we'll shrink this down, get it out of the way. Throw it up over there. And then now I'm ready to do the 6 centimeters from the blue in the direction of green. And that looks about right. So I'll walk, or he'll walk, to there. And then he walks 300 meters south, and that 300 meters is 3 centimeters. It's directly south, so you can just click this into place and put the 3. Now he was left off here, and they went 3 south, like that. And now he walked up and over in there, and he can draw, if we draw in his resultant vector, or displacement, draw in the displacement, we would draw it like that. And there it is. It's basically west, but it's probably like 180 a little bit more, like maybe 185. We're going to measure it. But the first step that was asked for, was what was the distance of his walk? How do we come up with that? We sum them up, don't we? It's just 600, or 500 plus 600 plus 300, which is 1,100, 1,400, 1,400 meters. So delta S is the distance with no arrow above it. And that was 1,400 meters, which is how many kilometers? 1.4. Okay? So now we have to find this displacement. To get that, what do I have to do? Where's the displacement on the graph? It's the resultant, the pink arrow, right? from Tommy's cabin to Annika's. And so we're going to measure it. We're going to get its centimeters first to get its magnitude. And I get 5, I can get it set, 5.5 centimeters. But I'm not going to write 5.5 centimeters. I'm going to convert that to meters. And I'll see that I get 550 meters. That's the magnitude of delta S. Graphically, for the direction, we just use our protractor. Where'd it go? Oh, man. Now I got to find it again. Oh, there it is. So you just take your protractor and put it on there. Uh-oh. Don't want to do that. Don't want to change its shape. All right, when we put that on the tip, put the arrow in the tip, we see that we have 180 and plus about 5 degrees, right? See that? That's 90, that's 180, and then a little bit about 5 degrees right there. So that's 185. So we would say 550 at 185 degrees, and we'd be done. The direction is 185. Yes. Oh, you could say, in this case, the scale I gave you up there wasn't north-south, it was 0, 90, 180, 270. Then you could say 15 degrees south of west. Yes. For this one, for the graphical, the equation to do it is in the mathematical. We did it 2 different ways, graphically and mathematically, right? The mathematical involves getting trig, finding the sum of the components, right? And then doing tan inverse and Pythagorean. So we could have, with this, found all x and y components, sum those x and y components up, found the resultants by Pythagorean, and then tan inverse to get the angle. But we didn't. We did it graphically with a ruler and a protractor. No, that doesn't matter. You don't have to change it unless I say to. Meters would be standard. So unless I said to.